All right, thank you for the opportunity to speak. I'm sorry I couldn't be there in person, but I hope you're all having a good time in Trento. Yeah, today I'm going to be talking about a project I'm working on with several other colleagues. Slides won't change, there we go. Several other colleagues at Syracuse University and then also Lonel and IPNL. And that is to do a sort of a joint Bayesian analysis of NICER data and gravitational wave data. And I'll explain what I mean about that in more detail. But basically, the main idea here is, as we've seen from several of the other talks, you get good, much better constraints on the equation of state if you combine results from various telescopes and gravitational wave data. But most of the things that have been done previously is to take the posterior, the output of, say, the gravitational wave data, and then combine that with the posterior from the NICER results. Here, though, what we're looking at doing is just doing a giant Bayesian analysis where you analyze both the NICER data and the gravitational wave data simultaneously. And the reason we want to do that is we're particularly interested in seeing if we can get different evidence for different hotspot configurations on the NICER side, which then maybe will lead to different equation of state constraints. Now, everything I'm going to talk today is very much a work in progress. So I don't really have concrete results to show yet, and I apologize for that. But so this is more going to be a proof of concept technical talk, but hopefully you'll still find it interesting. Okay, so a little bit of more background here. We've had some very nice talks about the equation of state with constraining the equation of state with gravitational wave data. Garrett gave a very nice talk earlier today. But just to recap, a few years ago, myself and several colleagues did this paper where we took chiral effective equation of states from chiral effective field theory that was provided by Ingo Tooze. And we use these to reanalyze the GW170817 data, where we assumed a common equation of state between the two neutron stars in that system. And in that paper, we used two sets of equations of state, one where for the low density part of the equation of state, we use chiral effective field theory. And then at some point, we transitioned to just doing a piecewise extension in the speed of sound plane. And we had two sets of equations of state, one where we did that transition at nuclear saturation density, which is I have plotted here on the left, and another where we did the transition at twice nuclear saturation density. And essentially, Ingo provided us a bunch of equations of state, 2000 to be exact. And we then just did our Bayesian inference, where we sampled over those equations of state to get the tidal deformability for each of the stars. And then doing that, we were able to get a posterior on the radius, and that's what's shown here. So this is mass versus radius for that. And each one of the lines here is the various equations of state we had in our prior. But here, the darker the color, the more favored that equation of state was in the posterior. And so up above, we had the 1D marginal posterior on the radii of the two stars and the masses, and the same thing for the other set of equations of state. And these two essentially mostly sets agreed with each other, and essentially we then pulled out of this a estimate for the radius of a 1.4 solar mass neutron star, and we got roughly 11 kilometers plus or minus 1. And this is a 90% credible interval. Okay, so this was back in 2019 when we did this. But then since then, we've had a lot more data come out, particularly there's been the NICER results. And with those, the constraint on the 1.4 solar mass radii has been going the opposite direction, going to more larger radii than what we got in our result. This is a plot that I stole from a talk that David Radici gave at the AI last year. This was in early 2021, so this is already out of date. But you could already see here our constraints, which are in the middle here, are on the low end compared to other ones. This is in a chronological order of when the papers came out. In particular, you can see, well, we're around 11 kilometers. Later papers are getting up more around 12 kilometers. And a reason for that is, a big reason for that is the NICER results. So this is showing a plot where I've now shown the same plots from the first slide, but now I'm throwing on top of that the posterior result from the first NICER analysis of PSR J0030, and that's shown in the green. And you can see that the NICER result from the first one very much favored much more stiffer equations of state, so higher radii. But now, granted, the uncertainty was quite large from the NICER result, but you can see in general the overall posterior was more favoring something different than what the gravitational wave data was favoring, and this has pulled the radius constraint to higher values. And then since then, more results. There was the second NICER analysis on J0740. That was a higher mass neutron star, but also had a radius of around 12 kilometers. And so the result has been things going more towards 12. And this is sort of a nice sort of summary of how these different analyses are stacked together on the left here. This is from this Dietrich et al. Paper, where they do something very similar to what we did. So they have these sets of equations of state from parallel effective field theory. But here they sort of did the opposite direction. They started with the NICER results, get a particular constraint, and then throw in the results from GW170817. And then here you can see what the effect of the constraint on the radius is as a result. And you can see NICER pulls it up to 12 kilometers, and then the gravitational wave data tries to pull a little bit back down, but stays up around there. And then again, throwing in more data, and more subsequent papers, we're getting something more around 12 kilometers. Okay, so were we then completely wrong with our initial analysis? I have to say I did find these sort of constraints going to higher radii a bit surprising. If the NICER results had said that the constraint was more towards softer equations of state, more lower radii, I wouldn't have been that surprised about that. The gravitational wave data wasn't very informative on the softer end. In fact, you can't, from the gravitational wave data alone, distinguish whether or not the two objects were neutron stars or even black holes. But the gravitational wave data was fairly conclusive about the stiffer equations of state. You can see that in my original slide here. The light gray here was our prior, and you can see that the larger radii, the stiffer equations of state, were very much ruled out by the gravitational wave data. Now, one thing to keep in mind, though, with these NICER results is they're dependent on, they have to figure out what the hotspot configuration is on the star that they're observing. And Garrett talked about this a bit earlier. Essentially, though, you have these hotspots where the X-rays are being emitted from, and that's the thing that the telescope is observing. And so to figure out what the radius is, and also in the case of J0030, what the mass is, you have to figure out what is the configuration of the hotspots. Where are they, the number of hotspots, where are they on the star, and their shape. And what you get for those results affects what your mass radius posterior is. So this is a couple plots from the Riley et al. Paper on the first event, J0030. On the left here is what they call this STPST configuration, which turned out to be their favored one. And you can see the configuration they ended up with was two hotspots, one where you had essentially a circle, and then the other one was kind of splayed out. And both of these were on the hemisphere that was opposite the side of the observing angle. And this down below is what the posterior they got on that was, and the first column here is the radius. But just as a counterexample, if you change the hotspot configuration, so here was another configuration that they considered where it was two spots, but both of them were circular. From this analysis, they got a very different radius. In fact, they got a radius of 10.4 kilometers. You can see though that the mass, it was favoring much lower mass. In fact, was railing against their lower bound and their mass posterior. Now, this model on the right was very much disfavored compared to the model on the left. If you calculate the Bayes factor or the log Bayes factor, this one is favored over this one by a log Bayes factor of 9.4, which is very, very strong. But it does just highlight that if you use different configurations, you get a different result. And most of the results that have looked at combining gravitational wave data with NICER results have just taken the most favored models from the NICER only analyses and then combined them with the gravitational wave data to get equation of state constraints. But it does raise the question, when they did these NICER analyses, the prior that they were using just arbitrary input priors. It does raise the question though, if you use priors that were conditioned on the gravitational wave data, would you get a different hotspot configuration being favored? If you ended up getting a different hotspot configuration being favored, would that lead to a different equation of state constraint? And so that's ultimately what we want to try and investigate here. Okay, so how can you do this? How can you condition the NICER results on the gravitational wave data? Well, one option is you simply take the posterior on the equation of state. In our case, where we had just an equation of state index, that would be the posterior on the equation of state index, and you use that as a prior for the NICER analyses. And then you would just repeat the NICER analyses for each one of your various hotspot configurations, recalculate the Bayesian evidence, and see what you get. The one problem with this, though, is it's kind of difficult to get Bayesian evidence this way. In particular, the sort of standard way to get the evidence is to use nested samplers. But the sort of standard ones like multi-nest dynasty, they can't take as input arbitrary prior distributions due to the fact that they need to have a quantile function for the distribution to be able to work. There has been a paper recently that was talking about being able to input arbitrary priors for dynasty, but it involves using machine learning, et cetera. It's complicated. Another solution is to just use a Markov chain Monte Carlo, where you can input arbitrary priors, but in order to get evidence values from MCMCs, you have to use parallel tempering. And this is computationally expensive, and it's also not the most robust evidence estimate. Generally, it's difficult to get a good evidence estimate from parallel tempering, at least not without throwing a lot of computing at it. Another option is you just jointly analyze the gravitational wave and NICER data together. And what I mean by this is, instead of doing your separate Bayesian inference analyses, your separate parameter estimation analyses of the two events, say G2 170817 and one of the pulsar separately, you do one Bayesian inference analysis where you analyze both of these together. So instead of say 15 parameters in your parameter space, you have now 30, because you've essentially doubled the number of parameters from both. The advantage of this approach is that you can use now this standard nested samplers like dynasty and multi-nest because you're just using analytic priors as the input. Another nice advantage is you can get better constraints in all parameters and potentially learn about maybe some unexpected correlations between various parameters. But also you can get the evidence values for different input configurations, which is what we're after. There are challenges to this, of course. The big one is that this isn't very scalable. So, because each event that you're adding in is adding many more parameters to your analysis, your solution, your parameter space grows quite quickly, and this makes it much more difficult for the samplers to converge. But for a few events at a time, this is doable, and that's the sort of scenario we're in here, where we really just want to at least take GW 170817, which has a lot of information in it, and combine it with one or both of the initial 2 pulsars. But another challenge to this is doing one of these joint analysis requires combining code and analysis methods from different disciplines, which requires different expertise, and it also involves combining different codes. And so in this case, we're talking about gravitational waves and X-ray astronomy. Now, there are work going on writing software suites that can take in information from these different type of detectors, one of which is this paper by Pang et al. But this is a challenging thing to do. In particular, there's a sociological challenge to this, and that's that nobody likes to use other people's code. So each of these different analysis pipelines, you have different experts in these different things, experts in gravitational wave data. They've written their own analysis codes to do gravitational wave parameter estimation. You've got people that have worked on X-ray telescopes in NICER and have written their own software suites. And if you want to do one of these joint things, you essentially are talking about either throwing all that out and starting from scratch with some grand software suite, or somehow getting one of these software codes to sort of swallow one of the other ones. And there's technical challenges to doing that. But what I'm going to talk about here is a method to sort of combine these different things without actually needing to merge together various software codes. And before I do that, let me tell you a little bit about the software that I work on. I come from the gravitational wave side of things, and I work on this thing called PyCBC Inference. It's a part of the larger PyCBC package, which is this package that's a Python package for analyzing gravitational wave data. It initially started out as for doing searches, and it is one of the sort of main searches that the LIGO, Virgo, and Cagra use in their analyses. But we also have a Bayesian inference component to it. And we've had this Bayesian inference component for several years now, and we've had quite a bit of success with it for doing different things. And one of the nature of gravitational wave problems is that because we're tackling many different problems and having to use different waveform models, it's forced us to sort of make this code very modular, because one day you want to just get the masses and spins of a binary black hole. Another day you want to do black hole spectroscopy using ring downs. All this, what this means is it really has forced us to break things down into the steps of Bayesian inference into their components, and sort of try to abstractify that as much as possible in the code. To sort of give a visual representation of that, this is a call graph showing what PyCBC Inference looks like. I don't mean for you to understand all this, there's just a lot to in here, but this is just to highlight that these different steps of doing Bayesian inference is broken out into different modules in the code. So you have a module that calculates the prior, you have a module that generates the gravitational waves, another one that calls out to the stochastic sampler. And then all these steps are stitched together by these model classes. And essentially by changing the model class, you change the problem. And so the standard thing that we have in PyCBC now is we've got models to do standard gravitational wave parameter estimation, and we have other models to test GR, do black hole spectroscopy, et cetera. But one side effect or one advantage of this sort of abstraction is that if you simply swap out the model, you can do other things. In particular, you're not tied to just gravitational wave data. So you can imagine adding another model that calls out to some likelihood function and some other package like XPSI that analyzes NICER data. You let XPSI do all the work of analyzing the NICER data, you get back a log likelihood, and then you can combine that with your gravitational wave data and give that to your sampler, and then you can do this grand Bayesian inference. But even doing this, calling out the log likelihood, you would think you would need everything together in sort of one software suite, which again, you have this challenge of stitching things together. But one sort of nice thing about Python, and I'm not sure a lot of people know about, is that Python has this ability to create plugin packages. And what I mean by that is you can have two completely independent software suites. And then you just write a little thing that's independent of both of these that essentially takes one sort of adds it to an environment, and then the other software can automatically detect that and use it without needing the two things to actually be living under one umbrella. And we make use of this in PyCBC. In particular, we have support for making plugin models. And what I mean by that is, even though we may not have a particular model in PyCBC to use, if you write a small little, if you have some other software over here that says, say, analyzes X-ray data, if you write a little plugin thing for PyCBC that essentially wraps that up into something that PyCBC understands, you install that into your environment, and then a PyCBC Inference will automatically detect that at runtime, and now you can use that. And so what we're doing here is doing that with XPSI, which is the software suite that was written to analyze the NICER data and has been used in the Riley et al. Papers. And so even though this is completely separate from PyCBC, by sort of writing this little plugin thing that kind of stitches XPSI to PyCBC, we're able to use the XPSI likelihood in PyCBC and thus do a NICER analysis with PyCBC, even though PyCBC is a gravitational wave data package. And so we're currently working on doing this. This is still, like I said, a work in progress, but sort of as a just first test of this. Here I try to replicate the analysis on the second pulsar, J0740. So here in the orange contours here is my result, where I'm using PyCBC to sample the parameter space, but I'm calling down into the XPSI likelihood. Now you can see the results, they're close, they're not quite right yet. So in the blue here is the original published result on this event. On the left, I have the mass versus radius. And in the orange, this is the result from where I'm reanalyzing it using PyCBC, calling into XPSI. And you can see the radius, I'm getting a bit of a different radius here. The reason for that is I'm getting different results for the hotspot configuration. On the right here, I'm showing some of the parameters describing one of the hotspots. And in particular, this parameter here essentially describes the size of the hotspot. And you can see I'm getting a much smaller hotspot for that, a much smaller size for the spot. It turns out, I think the reason for this is due to just the version mismatch between what was used for XPSI, between what was used in the publication and the version that I wrapped up here. I talked to Serena a couple of days ago, and I think I know what to change on the XPSI side to get this to work. But at least in terms of just the framework of being able to run this, you can see we can do it, and it works fairly well. Okay, but that was just reanalyzing the NICER data with PyCBC. That's not that interesting because XPSI can do that on its own, and there's also the Miller et al. Code that can do that. But like I say, what we ultimately want to do is combine this with the gravitational wave data and to sort of do this grand Bayesian inference. How do we do that? Well, in PyCBC, we also have this hierarchical model, which is basically a model of models. And this essentially just takes the product of likelihoods from constituent models. And so we can use this then to combine our standard gravitational wave models with, you can really use it with any plugin model that you happen to write. In this case, we're doing it with our XPSI plugin to be able to do this grand Bayesian inference. Like I said, this is still a work in progress. As you saw previously, we have this bug in the NICER analysis, but just as a proof of concept, I did a run here where I'm doing the joint NICER analysis on PSR J0740 with GW170817. And this is sort of a corner plot showing all the parameters in the analysis. You can see down here in the lower right, this is the gravitational wave parameters describing GW170817. In the upper left, this is the parameters describing PSR J0740 from NICER, and actually also including XMM data in here. And this is all, the two are all linked together through the equation of state index parameter here. I don't mean for you to pull anything of interest out of this. Again, this is still a work in progress, and especially since we have this uncertainty in the this bug in the NICER side, you know, I wouldn't read too much into the results here. But sort of one interesting thing, sort of offshoot that you can potentially get from these things is looking at, you know, maybe some unexpected correlations between some of the pulsar parameters and the gravitational wave parameters. So for instance, one thing that I'm finding kind of early on is that because the pulsar data is favoring the stiffer equations of state, one thing that you can do to compensate with that on the gravitational wave side is if the neutron stars in the GW 170817 say had higher spins than what you had expected. And so sort of one kind of early result I'm finding potentially from this is that when you look at the gravitational wave data alone, you thought that maybe the spins of both objects were non-spinning. Here I'm plotting this sort of effective spin parameter, which is a sort of weighted average of the two component neutron star spin. But when you throw in the NICER data, it wants to pull that parameter up to higher spins, more positive spins. Again, this is only preliminary. I don't know if this result will hold itself, but it just illustrates the sort of new things that you can learn by doing this sort of thing on previous events. And with that, I'll just wrap up. So just again to say, by doing these plugin things, we're able to jointly analyze the NICER, the pulsar data using NICER and XMM with the gravitational wave data. And eventually we plan to test the various hotspot configurations, particularly with J0030, to see if, you know, when you're folding in more information from the gravitational wave data, if something else is preferred. Also would like to, instead of sampling over the single equation of state index, but actually sample over the equation of state parameters directly. This will add more parameters to our analysis, which will be a computational challenge, but hopefully a surmountable one. And just more generally, stepping beyond this, I think this thing of using Python plugin modules, whether that be with PyCBC or whatever other package that you have, to sort of combine information over these various software suites, I think this is a very promising way to do Bayesian inference going forward with multi-messenger astronomy. And I hope it's something that the rest of the field picks up on. And if you're more interested in how PyCBC works and writing your own plugins for PyCBC, we have a lot of documentation and tutorials on it at pycbc.org. There's also we have a email thread that you can send emails to, and also a Slack channel that you can join to get more real-time help and feedback. And so with that, I will wrap up and say thanks.